My mic is on, my chai is ready, and now all I have to do is test my audio levels. All right, I can hear myself. Perfect. Um, Hey everyone, welcome back to the Top Kaggle Solution Study Group. Quite a long name for something simple. We just gather every week where I try to condense top solutions as I learn them with you. And hopefully the end goal is we walk away with some insights from top Kagglers. So today's challenge is similar. It's not similar. It's a problem statement involving really long videos, games that are like 56 minutes, 57 minutes in length, and you're supposed to classify events inside of those videos. So if you clicked on this video, or if you're joining me live, that's what we'll be learning today, how to work with really long videos. And to put things into context, yeah, context is the right word. We had looked at TensorFlow Great Barrier Reef competition last weekend, and that had clips around 30 seconds, if I remember correctly. If you look at this competition, you'll see videos that are like 50 50 minutes long each. It's a 3 gig file. You can already expect a large number. But nice thing about Kaggle is they have somehow allowed you to play all of these videos. So if I zoom in a bit more, you can see that this is about 57 minutes, which is crazy long. So working with such video files is quite a challenge, and we'll be learning how to solve that challenge. Of course, the simple way is to convert all video files into frames and then you go from there. But if the video is so damn long, you end up just running out of memory. So let's see how the top teams did it, and let's just dive into it. Quick two announcements. I wanted to do like a celebratory speech, but nothing really. We hit 10,000 subscribers, so thanks to anyone who's been watching these. I've been teasing the NLP study group, and if you actually head over to the live tab, you can see that this is happening in 4 days. The author Lewis will be joining me. And to celebrate, oh, well, live, I can see myself live. And to celebrate the 10,000 subscriber mark, I wanted to do something special. So I'm gathering all of the absolute Kaggle legends together, and we're doing a quadruple grandmaster panel. So just wanted to tease those things out or just announce them. There's also a long-term project that I've been working on, which is writing a book, but I'll share more details on that. So the short version is I wanted to convert chai time into a condensed book that you can consume in like an hour, probably 2 hour, which is shorter than half of the interviews I've done. So I'm working on that book that will come out in about 3 months. It's not going to be monetized; it'll be free for all. But that's a long term celebration that I'm working on. Hey Shiva, Shiva has been joining us for 3 weeks now, so it's great to see you. All right, with that, let's jump into this competition. And I'm officially out of chai already. Anyways, the goal of this competition is you'll detect football, and they clarify it is indeed soccer, which I know nothing about. I started playing FIFA in university, and at that point I realized I'm better at CSGO, and I was better at trash talking there, so I just stuck to that. So I'm new to soccer, and I'll probably be speaking from my level. So I'm sorry if anyone is familiar with what passes are, what cross passes are, what a challenge is. So you'll detect soccer passes, including throw-ins and crosses, and challenges in original Bundesliga matches. Now I read up a bit about this, and if you know all of this, I'm sorry, but I'll just give you a clarification. There are different leagues where people play. The most famous ones are the high-level ones. Then there are the low-level ones. The promise of this competition is, hey, the most famous matches that happen in Qatar are like really high tech, but what about the lower leagues where everyone starts? So the goal is you'll help create ML models that will help at those levels. So these will help lower level leagues or more amateur leagues. Bundesliga, I think, is one of them, and the video recordings in here are amateur matches, which means people who aren't at pro level or like at the international level. I don't understand the clear distinction, but that is the plan. Someone saying it's nice to hear that you will get the books free. Of course, it'll just be one book and it won't be as lengthy. As it is, the the interviews are available for free. So what I'm planning to do is just condense them into a book. But you can just watch them for free anyway. So why would I like write a book that you might have to buy? Anyways, I digress. So your work will help scale data collection process, and automatic event annotation could enable event data from currently unexplored competitions like youth or semi-professional leagues or even training sessions. So as you can see, this like becomes really crucial because you can easily record all the matches. But right now, the host mentioned that it's just manual labeling of data so far. So by doing this, you'll actually really help a sport at different levels. Let's look at the evaluation metric. So submissions are evaluated on average precision of detected events. This is quite sophisticated, so I'll come back to this. But basically, you have to detect these events over the timestamps, correct? So you have to detect if it's a challenge, if it's a play, if it's a throw in, and you have to give the confidence intervals or the confidence values for these at different timestamps. There are ground truth values, and basically by comparing the overlap of those, you will be scored. I'll come back to this to explain it in a bit more depth because there are like 4 steps in which it works, but that's the like simplified version of it. So you detect events at every timestamp and it's compared against the ground truth. That's the simplified version. The cool thing about this was a second stage competition, which means that after the competition ended, it would be rerun on unseen test data later on, which is like new matches that are recorded. So the participants had to actually wait for 2 months to get the final results. Again, general code requirements less than 9 hours of runtime for both the things. Here they extensively define what the different events are. So I thought it's just either a play or like a pass. That's not true. There are like multiple subclasses as well. You just don't have to like classify simple events inside the video. There are a lot of classes inside there. So they've described what a play is. A play is a attempt to switch ball control from one member to another member. It may be a pass or a cross. A cross happens when you are shooting the ball from these red boxes to another area. A corner kick is when you're kicking from the corner. A free kick is when the game restarts from the kick. An open play is just happening anywhere apart from this. Throw in happens when the ball is thrown from outside the field to inside the field. Challenge is when basically they're like trying to challenge the person holding the ball or the person in possession of the ball, and the possession is being tried to the opposing team is trying to steal possession of the ball, or they're trying to challenge the team. Then there are like subclasses as well. Ball action carried out, was there a foul, opponent dispossessed, possession retained during challenge. So these are all the subclasses that you have to work with. It's just not as simple as, hey, there was a pass that happened, hey, there was there was just like a corner kick. There are fine nuances. So again, you have these incredibly long videos, right? Inside your training data, you have, it says 12 files which are each about an hour long. So 50 minutes is the first half, and then the second file is like the second half of it. So if you look at all the files, they are labeled 0 and 1, and that's because like 0 is the first half and the 1 is the second half of it. Also, if you like play these videos back, I'm not going to do that, feel free to, you'll see that these games start at like these recordings start at weird times. So sometimes it's like no one is on the field, people are starting to walk out, and they're like also practicing, and the match starts at a later stage. So you'll also have to deal with all that and put that into consideration. And you of course have labels for some of these parts, for some of these parts you don't have the labels. You were also provided with additional clips which are like much shorter. So this one is like 30 seconds, and you had about, how much does it say, 200 such clips, so 200 more clips to work with. Again, the goal is to identify what's happening inside the video at different timestamps. So I have this entire video where different things are happening throughout. It could be a challenge, it could be a play, it could be a throw in, and you're supposed to identify all of that. So here's an EDA of the competition dataset. I'll just sip some water and get back to this. Here you can see, and this is by Yaroslav. So I'll remember to upload his incredible work. You can see that these are the different labels inside the data. It's start, challenge, end, throw in, play. And 3500 is the max value, which is true for three of these. Throw in is like the least probable, surprisingly. And then he dices into, or he like subsets into how many times his throw in happen. You can see that when a throw in is happening, what's going on, how many times does a pass happen, or how many times is it a cross. And then for each video also he's like shown this, so these are like the video IDs, and he's shown how many times does a pass versus a cross happen. Cross, if you remember, is like those corner areas of the field from where the ball is shot. So he's shown us the plot of all of these things, and he's also very kindly shown what's happening inside the video. So I could spend my time playing back these videos to you, but then I realize in interest of your time, it's better if I just skip this, because I'm new to soccer. I assume you all would be familiar. If you are not, just go through his kernel. You'll see all of these things happening. So when it says a pass, you can play back the video and see what's happening inside the video. When it says cross, you can play back and see what's going on. Again, to remind you all, it's like when the ball is shot from these dark red corners. There are also subsets, right? So when a pass is happening, is it an open play? Or when a cross is happening, is it an open play? Or a free kick or a corner kick? There are also such subsets. Most of the times it's an open play. So like a dumb baseline could obviously be just just tell everything is an open play, and we'll see why that could be like a bit flawed to benchmark. So here are some more plots against, is it a pass in open play versus cross in open play, free kick, etc. As you can see throughout all the videos, it's very like common to see most of the events being passes in open play. And then trailing behind, I'd say the green bar, which is pass in free kick. Yeah, that looks like the second highest. So like as a dumb baseline, you could just like randomly predict those. How can you get Kaggle merge? It's best to reach out to Kaggle team. Or when you used to reach the Grandmaster stage, they used to give out these jackets. Now they don't. I think like if you also win some competitions, they're still being offered. So you can see these videos for like different subsets as well across when a free kick is happening. And as you can see, like there are many subsets. So you can play through these videos. He's very nicely made all of them available. I'll end this walkthrough of this kernel right here, but you're welcome to see like when is a ball action forced happening, or when is it a foul, etc. etc. Like I understood it's like more important for me to understand all of these things, and after that it's just like you have all of these labels for your model to work with. Yeah, I think that's all I wanted to point out. Now, another thing worth noting here is that many teams actually converted the images into black and white. So when you do that, you like make it easy, first of all, computationally to work with such stuff. Why is that? Remember when you feed in images to a CNN, it's three channels, red, green, and blue. Now you're just feeding in one channel. So like the dumb way of, or the not dumb, the simple way of doing that is like when you're working with black and white images, you just copy the channels over to all three channels, right? RGB is just black and white, black and white, black and white. But if you're like specifically doing that, there must be a reason. So what some teams or most teams ended up doing was they converted their image into black and white. Now this is like a video, right? So video has images in sequence. Very obvious. Thanks for pointing out. Don't be mad. So what many teams did was instead of RGB channels, each channel became a frame. So T plus one, T plus two. That's like RGB. And some people did like variations of that. There were some 2.5D models being used. There were 3D models being used. The other cool thing about that is, as you can see, Yaroslav here has done like some post processing, and you can like also identify lines. You can also identify players very easily. You can also try to identify the ball, which is like identifying the ball is key here, right? Because that's where like most of the interactions are happening, and that's what you want to pay attention to. So all of these things are worth looking at, worth paying attention to. Let me just catch up on the chart. Arun is saying Congo and 10K. Thanks, Arun. And hey, Mayank. Mayank has been regular now. He promised me he'll keep coming back to live streams, and I'm happy he's been coming back regularly. So that's great. This is the like most popular kernel that had been shared. So it was again um, called benchmark training, and this was by Tito. So he shares a simple benchmark script for DFL. It classifies each frame into four classes, and it does not use any temporal information. But he says, in his opinion, this is a good starting point. So he's defined tolerances trained for approximately 100 epochs. And here's a cool thing, right? So, like, the next obvious question becomes how are you setting up the validation folds for videos? The top team, and I don't think other teams pointed out, but the top team set two videos aside for validation and kept checking on that. And I think they had one more for testing. So that's what they did. That's what Tito also showed in his notebook. So if you have a lot of videos to work with, this is one possible validation split. You can have just set two videos aside and all of the rest become test. Sorry, train, not test, train. You're training on all of these and you're validating on two of these. And at the end of it, whatever model you have, most top teams end up retraining it on the entire data set. So that's also pretty common. So he's loaded up the data set. He's told you how to work with the training images. And finally, he's trained, like, shown you how to train a B5 model on all of these. So this was like the only baseline, if I remember correctly, shared that taught you how to work with this data set. There are also like specific ones teaching you how to detect the ball using YOLO V5, and Tito, by the way, had also shown you how to run inference with this notebook. So it was like two notebook baseline. So other people had shown you how to do ball detection using YOLO V5. I'm skipping this, but you're welcome to read through it. So these are all the baselines that were shared with the model, with the competition as it started out. Now, what I want to do is I'll do a quick refresher of some concepts through Hydrogen Torch, and hopefully I can share the correct screen this time. Yes, I did it. Sumit is asking, how's everyone? I think everyone is tired today. So, what I want to refresh everyone's memory about is how do you do object detection and general image classification. So let's look at this data set for object detection. Now, if you've seen Team Hydrogen, they're always on top of LBs, and this basically contains all of their insights. So it's a nice way to also showcase all of these concepts to you. So what I've done here is I've loaded up a object detection data set. And as you can see, it allows me to simply visualize everything. I can see that, hey, the identified boxes are all wheat, and it lets me hover my mouse over them, interact with them. It also shows me the statistics and some summaries of it. And from here, I can create an experiment just through a click. And I can say, hey, I'm like feeling very, very brave today, so I'll work with the master setting. Or if you like want the most easygoing settings to start out with, you should go with novice. That's also very easy to do. So inside object detection, you have different model types, which could be efficient det, faster RCNN, and FCOS. We had seen FCOS last weekend, if you remember, in the TensorFlow GBR competition, and also faster RCNN. Efficient det is also pretty popular, and I'd done a paper reading group on this a while ago. So I think this was these what at that time. I'm not sure what is today. So from here, you can define your validation strategy. Now, what I'm doing here is I'm working with images. But if you're working with videos, it's just videos that end up getting converted to images, right? And I need to pass in the column that's I already identified all of them. I can set the image width and height. I can set the number of channels. So if I was just working with black and white images, I would set this to 1. Or I can set it to 5 if it's like a 2.5D problem as well. It'll identify that. And then I can select the image normalization, select the augmentation strategy, and I can enable cut mix. So from here, I can also select the backbone. So it could be efficient det D0 to D7, and it could also be mobile det or different backbones like so. A cool thing about this competition was, since the videos were so less, so it was not as many videos, right? We just saw 12 videos. Larger models were overfitting quite a lot. So this was shared throughout the competition, and there was a risk of overfitting. I can set the optimizer learning rate. I can also enable differential learning rates. And if I want to make sure my model does train, I can enable this cool setting. And from here, I think I'm all set to kick off this experiment. There are some other things worth pointing out, which I'll quickly do. You can also set the IU threshold and maximum number of detections per image. So if I was just working with ball detection, I would set this to 1. So internally, what would happen here is it would look at the most confident prediction and just showcase that. So as you can see, through all these simple clicks and selections of menus, I've queued this experiment to run. And I've already run another experiment on object detection, and it makes really easy to look at all of this. So after doing all of that, you can investigate your insights and take a look at the plots. And you can also take a look at the validation plots and best validation versus worst validation samples. So for object detection, you would want to look at the confidence versus box plots. One of the competitor had shown that you also need to be careful when you're using image classification. So image classification usually allows you to investigate with GradCam, which shows you a heat map of how the images are being detected, or what part of the image is making the model detect the flower inside of it. So you can see that it should ideally be around flowers, right? And for best examples, it will be around flowers. So some competitor had shown that, hey, while you are trying to identify events, it was just looking at the crowd and not at the players at all. So it's also important to look at all such grad cam visualizations and make sure you're working with them in the right way. So I just wanted to use hydrogen torch as an excuse to first of all show this awesome framework and also remind you of all of these concepts and things you need to pay attention to. And it's quite convenient because all these models essentially train in under 2 minutes. If you want to check this out, you can head over to our website and read more about it there. I'll switch back to sharing about Kaggle discussions now. Give that 1 second. Select my right window. Make sure I don't share any other window. Awesome. Shiva is saying we're all doing great Kaggling. That's great to know. Which competition are you taking part in, Shiva? Yeah, let's find you on the leaderboard. Just tell us which competition you're on. We'll try to find you on the leaderboard. So that was the refresher I wanted to give you all for object detection and image classification, both of which are like the foundations of working with this competition. So as I mentioned earlier, this was like a two-stage competition where you had to like submit your predictions, and then later it was like rerun against a new data set. So it took about 2 months, and this is what that post is about. The cool thing that I wanted to point out in this competition was the test set was exactly the same length. The like later test set was exactly the same length, while same length to the earlier test set. So I need to clarify that when such two-stage competitions happen, you have one private, which is revealed later on, and you also have the public LB on which you rerun. So the final private LB is usually revealed right at the end. And it could also be rerun in multiple stages. So, for example, when I took part in AI for Code, it was rerun thrice. So that also makes it challenging, and you have to sometimes account for like the differences. So what if like it has three additional videos and you're like right at the edge of 9 hours of inference? Then you have to account for the fact that hey, maybe you need to like not ensemble as much and like leave some time out for all of that. So all of these things also are an added challenge to all other things that are happening inside this competition. Now let's start getting into some roots. Moth in this discussion explains video classification. A video can be simply considered a sequence of images. It's a 4D tensor where you have the time into 3, which is RGB or height and width, time dimension, RGB, height and width of the image. In this way, you have one temporal dimension and three space dimensions, and then you can classify different things from there. The challenge here is the videos can be really big. So this competition had videos in 25 frames per second, which meant every second had 25 images in it. And videos, he says, usually can be 30 fps or 60 fps. I live stream at 60 fps, a little noddy detail. I don't know. I like 60 fps. And if I could, I would watch everything at 144 fps. But that's just not possible. Movies don't come out in that, games do. Sumit would know. We chatted about Dota a while ago. Training on clips, usually we have very long high FPS raw videos. However, to train a model, we will classify short clips with low FPS. Then at test time, we would take this trained model and apply it on different clips and average these predictions. So he suggested some approaches around it, late fusion, CNNs, early fusion. I don't think a lot of these techniques were used during the competition, so I'll skip past that. But these are the challenges that involve working with videos. Let's take a look at this discussion. So Tin Maro had shared a ball detection YOLO V5 model where I think he had annotated the images by himself and shared it. So this was quite important. And if you go through the videos, it's like insanely hard to spot the ball as well. So this is quite key to the problem, if I may. Vadim is back, everyone. Great to see you, Vadim. How are you, friend? It's been a while. Vadim doesn't pop in every now and then. But apparently, I spoke Dota today, and Vadim just popped into the stream. Is that what it takes, Vadim? So there were some discussions around SoccerNet dataset as well, which some people use, some people didn't. So there were additional challenges around what data sets people were using or not. I don't think top teams ended up using any extra data set outside of the provided one. And this is another trend I've seen, like many a times in very few competitions and external data is helpful. Most of the top teams don't end up using external data. So take what you may. Maybe you can tease them, maybe you can correct them, but I found most of the top teams don't use a lot of external data all the time. So in this discussion, the host from Kaggle had taught you that there are different ways of seeking the frames and video splitting. The best way would be ffmpeg. So you might be tempted to like just use CV2, and that was my like original understanding as well. Hey, CV2 OpenCV is like the best framework. I'll just use OpenCV, it's the best. There are issues around it. So you need to like figure out what framework is best, and you need to like also make sure when you are separating your video into images, you process that in the right way. So now coming back to the metric, I had promised that I'll come back to the evaluation. The challenge was with each video, there is a defined set of scoring intervals over which you would be scored. This was not revealed to you. And during the competition, you had to, of course, go through the entire videos. So this was an added challenge in the sense that you were not told the prediction intervals, and these could be random, these could be throughout the videos. But the host had defined seconds, minutes where they really cared about what's going on in the video. I think like to make sure a model is robust or something like that. And you had to also account for all of that. And this was the discussion I had pointed out. So I had like the cool chance to showcase hydrogen torch to you all, but you also have to be wary of what is like really exciting the model. So you can see here that GradCam for efficient V4 with whatever settings Moth was training them with actually is just like looking at the entire image. So It's being activated by the roof, by the crowd, and instead you need to like really make sure a model looks at the ball, which is somehow visible in this frame. Usually, like it's hard for me to catch it, but it's right here, and that is like not doing anything to the model, as I understand. Same for this as well. And he says we can see that the CNN is paying more attention to things it shouldn't. So that was another showcase of why GradCam is important. Michael had shared a discussion around general strategy and pipeline. So he suggested, and I wanted to point out because this is like a nice first baseline, and then we'll see the second place solution by KMAT, which was absolutely awesome. So you could either start by saying, hey, is the ball visible in the frame or not? Then you can detect the ball and the players, and then you do some time series processing. After which you can identify what's happening inside the video and what play is happening. So this was the baseline he suggested. We'll see two teams in the solution share that had like approached this in a multi-stage fashion like so. But we'll see that later. I'll upload this and move on. This was another trick that I learned from Burke, who also learned it from another competition. So it's like a recursion cycle. But if you like basically want your models to be finished uploading in like a second, you can use this trick where you just like make it run if it's being rerun, and otherwise you don't run it and you just like leave it like so. You can read through it, it's quite neat, but that just like saves you some GPU quota. All right, so now we're at the part where we look at the leaderboard and see the scores, figure out how team hydrogen scored an insanely high score, and they were first on both public and private LB if I remember correctly. So you can see that there's like an insanely high difference here compared to other teams, and you can see like it's very consistent the drop across all top teams. So silver, highest silver is 6.4, and then it's 6.8, and then it goes all the way up to point 0.9. KMAT was second, Camaro was third. We can see his score is about 0.83, and you can see all the drops here in score across different positions. So for reference, we'll remember that zero point 0.6 is like a silvery score, and above 0.68 is like a gold score when we're looking at the models. Could I send this link? Which link are you talking about, Vadim? So let's look at the first position solution by Philip Singer. The team was all three of my colleagues from H2AI, and they usually like it's no surprise they're always like in the top five of any competition, like regardless if they're solo or teamed up. Um, can I send the link with the trick? Sure, let me just look up this competition's discussion with saving GPU time. If I post the link, it's like too damn long to show as like a pop-up. So just like go to discussion, search for saving GPU time inside DFL. So here's Team Hydrogen solution. They usually are always in, not usually, they're always in top five. And if you like actually look at Philip's profile, I don't think he scored his first bronze medal yet. So he was joking in one competition that he's yet to like score his first bronze medal. But they're absolute legends and always end up high on the leaderboard, is what I was trying to say. Cool. So here's the solution. They say it combines single stage model with 2.5D and 3D data to properly extract time related info from the video. The solution ranked first both on public and private LB. Here's the overview of their solution. So, for validation, as I pointed out earlier, they had used three videos for validation. Sorry, four videos for validation, and they had fixed train and validation split throughout the competition. Their best local score was 0.85. On LB, they scored 0.9. if you remember. And they observed strong correlation between local validation and LB. For final submission, they retrained their best models on full data. And this is a general process they say they always try to follow. The model setup, they say it's solely a single stage architecture. And this is because if you look at the second place solution, you can see it's like three, four, five, five step approach. So Team Hydrogen used a simpler approach, a single stage model. The input was 1024 by 1024 grayscale images, and they had stacked channels in time dimension over three neighboring frames. So as I said earlier, it's T plus 1, T plus 2. Ayushman is back to troll me again. Ayushman is always starting a riot in the chat, and I'm eagerly waiting for the chat to explode now. Go for it, Ayushman. He's one of the best computer vision practitioners in India, as I understand it. So I'm always I'm always happy to see him start a riot in the chat. Um, they chose grayscale images rather than full color due to improved generalization and runtime capabilities. And they said it worked really well on unseen dataset as well. The single stage architecture combined 2.5 and 3D techniques. Now, what does this mean? They said that they had used 2.5D and 3D approaches, right? 3D convolutions. We had looked at this a while ago. Check out the TensorFlow GBR competition if you uh, didn't watch that video. Like the live stream I did 2 weeks ago, I explained all of that in depth. So when you're doing this, you need to convert the modules inside your network, right? You need to like replace, sometimes you have to like also replace the normalization layers and make sure all of those can work with the data. So that's why like this is relevant to know. The backbone was efficient B0 or B1. And as I was pointing out earlier, the larger backbones tend to overfit quickly. Is this text size good enough for everyone? Because I always find like am I not like too zoomed out? I just want to make sure. Let me know. They say 3D convolution were only used in the last block and final convolution before pooling, which allowed them to stay in 2.5D for most of the backbone. So this allowed them faster inference times, and that's one of the like key reasons. If you like go into 3D, you can expect more runtime, and you're like limited to 9 hours of inferencing, right? And they had also like done some other techniques to speed up their inference time. They say, let's say like you're looking at t is equal to 15 frame, you would stack the three neighboring frames. So you look at t minus 1 and t plus 1 as the channels of input, and then separately pass five different timestamps. So if your timestamp would be 3, this would mean you'd like pass in all of the neighboring brackets as well, covering other frames. Key thing to note, these don't overlap. So for one team, this was overlapping. The other team, it did not overlap. Filippo is saying, can you share the link? I could, but these links are really long. So all you have to do is like go to DFL competition and just search for first position solution. It should take you there. If I highlight it, it's like too damn long to copy and paste and type. So that's why like I don't share them. Just go to DFL discussion first place solution. So you have these stacked throughout through the backbone, and the final 3D layer combines these five timestamps with additional pooling. They say 15 was the like best sweet spot, and that applied the usual set of augmentations and mix up as well. The loss function was cross entropy because you're like doing different classification. You have different classes. It's uh, not a regression problem. With three target columns, they said they could have improved on hard or soft labels. Of course they have to say that, right? Like they beat everyone with a nice score and they're not happy. It's like that annoying kid in class you see every time, right? Oh, I got 99%. Not happy. I could have done better. It's like that 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 kid everyone hates in the class or is jealous of in their class. Not hates. You're jealous of such people for good reason. They said they spent all of their time on training only the labeled regions. Pre-training helped, but they had no success with pseudo labeling. So during inference, they increased resolution by 128. What does this mean? They had trained on 1024 by 1024. Uh, they say this right here. So they increased it to 1 2. I don't want to mess up my math. They added 128 to both of these, whatever that ended up being. Yes, I'm slow in math. Which slightly improved their CV and LB scores. They spent a significant amount of time improving how fast can they run this, and they got it to like an insanely impressive 2.5 hours per model runtime. They say they predicted only every second frame for single model, and their final solution blended results of two models, alternating between them frame by frame. Then they applied post processing to reduce the number of false positives. So when we were looking at Hydrogen Torch by Team Hydrogen, we saw that you could do some post processing, like you could limit the number of detections, you could set thresholds for this. You could also work with the image and like do some post processing where you like detect lines, apply Gaussian blurring or stuff like that. They don't clarify what they did, but I assume it was something along the lines of fixing the confidence threshold and stuff like that. In the discussion, I wanted to point a few things out. So, not my tabs, but this discussion. They also experimented with TSM, GSM, and GRU, but they said the simple layer was effective. I think that's the end of it. They had also clarified what they meant by T is equal to 5 and channel is equal to 3. So this discussion clarifies that. But that's it for the first place solution. Really simple, really elegant solution, insanely high score, insanely optimized inference pipeline. To summarize, they trained on grayscale images, converted that into like a three stacked layers with five adjacent frames being passed to the model. After that, they run inference with very optimized pipeline and win the competition by a large margin. Let's look at the second place solution. And whenever you see KMAT, I will try to interview him on the channel because I'm always fascinated by his like insanely awesome solutions. If you remember, we had like read NFL competition earlier, and his solutions are like always really elegant, really high. Really depthful, is that a word? Really in depth, if I may. Yeah, that's the word I'm trying to get across. What did you use for these optimization local machine with GPUs? I did not compete on this competition. That was the first team solution we were reading. They had used a machine with three A6000s, as they mentioned uh, in the discussion, which I don't think is crazy for top teams. I've seen I've seen some top teams use like much larger compute than that, which is totally fine. Like that's what it takes to like squeeze out every bit of performance, right? Especially with videos, like I'm at least not surprised at all. So this is the second place solution by KMAT, and his pipeline consists of optical flow to get global camera motion, ball detector to find a ball on the field, cost minimization of ball trajectory to refine the ball locations over multiple frames, action recognition, and finally ensembling and post processing. So here's like a architecture overview in the image, and Kmat always draws these like really elegant images to make it easy for all of us. And he says like the key for him was cropping near the ball for action classifier. So I have the video with the RGB frames. Kmat worked with the RGB frames apparently. He passes all of these in, applies optical flow and semi supervised raft algorithm. It's one of the optical flow algorithms. You can read about it. From there, he takes the difference and passes 9 channel input into a center net to detect the ball. From there, he draws a heat map and takes the top 10 peak candidates, which are then stacked together. From there, he takes the temporal sequence of the top 10 candidates frame by frame and finds the best path using Dijkstra's algorithm. You thought this might never be relevant in the real world. You can see one use case where it is. So he stacks all of these together and finally does action recognition. And this is like surprisingly easy, right? Relatively speaking. Now, normally you expect like a crazy 2D CNN model with like 3D 5 channels. I don't know, some crazy thing, but like this is slightly simpler in that sense. So Kmart focused all of his approach around first of all detecting the ball, then figuring out what's like the best path the ball is following. Why is that relevant when you're like performing these? When you're not performing, when you're trying to identify the plays inside the video, you need to identify where is the ball moving along the players. Naturally that makes sense, and Kmart found out while experimenting, and he focused on that. So he did action recognition after that using a shallow 1D CNN, which is why I say it's like slightly simpler. And then he applied post processing as a Gaussian filter and peak detection. So he shares some more details on the left side. You can read through that, but I try to simplify and explain his architecture. So let's read through it step by step now. For optical flow, he says it's difficult to detect the ball when it's hidden behind the player, the background is the stand, or the balls are not placed on the sideline. So his idea was to use multiple frames to detect the ball, and he explains how he did that here. He used Raft to predict the optical flow, and it was provided video by the self supervised manner. After that, he detected the ball. He repeated training and annotation several times, and he selected center net because he does not like annotation. Annotating point is much easier than a rectangle. So the inputs consist of 9 channels, normal RGB, difference between current frame and previous frame constructed by optical flow, and difference between the current and next frame. He says these two drastically improve the accuracy, especially in crowded scene. And he shows an example where, like, I can't tell if that's the ball, but this helps the model, and you can like apply reverse logic. That of course this makes sense, right? Like this is what you would do. I mean, not me. This is like insanely hard to come up with such a solution, right? Like what I would do is I'll probably like train a Resnet 50 on this and call it quits because I'm on public 500. But that's the difference between legends like Kmart and me. That's why I want him to like. That's why I want to get him on the show. So I'll try my best. Try to interview Kmart next. After that, he performed cost minimization of ball trajectory. So he says ball location can be estimated more accurately by multi-frame information. He applied cost minimization on selecting the ball path, and this allows you to estimating where it will go next. After that, he performed event classifier classification. I'm skipping some details because it's really in the weeds, but I'm just giving an overview. That's like enough relevant, and then you can read through. So for event classification, he used the ball trajectory and images cropped near the ball over 1 second. Since the labeled intervals are short, it is difficult to make long sequential data. So he extracted only 1 second frames randomly. The model consists of 2D CNN to extract features, 1D CNN to extract features from ball path, and 1D CNN to predict event from upper two sets of features. He gives a very nice overview of the approach if you want to read through it. Then there's a second stage image event classifier. He says first classifier cannot predict long-term information. So he uses 4 second intervals that can be adopted because inputs is only feature vectors. So he extracts the feature vectors, I assume, from the previous stage and passes them into the next stage. For post processing, he had done peak detection by max pooling and Gaussian filtering on the challenge score. And then he shows the plot of how this works. He says, since the number of samples is not so large and most of the area of the image is useless, he thought the model would be hard to learn. So that's why he decided on the ball trajectory. Really insane solution and crazy level of detail that's gone into this. That's the least I can say. And I think this was like the most upvoted discussion in this competition for good reason, right? So if you read through this, or if you're like watching live or watching right later, just like remember to upvote these solutions. All right, let's move on to public third, which also ended up being the private third, and this is by Camaro. His baseline is a very simple end-to-end 2.5D model. Backbone is an efficient net with TSM. What is a TSM? He refers in the footnotes. So let's scroll there. It's a temporal shift module. Let's check out what that is. Temporal shift module for efficient video understanding. And we can check this out later. But they got inspired through this repository, and I assume they use some information from here. This was a paper from ICCV 2019. So he had used efficient backbone with the time module, and the head is a simple 1D unit. So it looks like he's combining 64 frames into passing that into a 2.5D CNN. And from there, he's applying NMS to get the scores and classifying that into a play. Next, he shares details. So for training, he pre-trained with ball detection. He says even though I had used ImageNet pre-trained models, inserting TSM module changes the structure. So he used ball annotation in the soccer net dataset to pre-train the model. It was set up like so. So efficient plus TSM plus contour head. Output is the same resolution as the final feature. And label is a 2D Gaussian heat map. But he didn't add regression branch. At first, he had annotated the images himself, but it ended up being a lot of frames, so he just ended up using SoccerNet. And this is what the results ends up being like. You can see that the ball is identified nicely. The labels are designed like so. So he used a 1D Gaussian heat map plus minus 5 frames along the event. He shows an example here. For sampling, he had half positive or half negative examples. Positive means at least one event, and negative means randomly sampled from interval. He shares the augmentation. Nothing crazy stands out here. The model architecture again is efficient plus TSM. Simple 1D unit, some variants of LSTM and GRU, and he ended up using layer norm instead of batch norm in unit. He says because batch norm didn't converge, maybe due to small batch size. Base loss is focal loss for him, and he had modified how the class balance loss was defined. After training with short clips like 32 frames, he had fine tuned with longer frames, but he had frozen the backbone to fit it inside the memory. He says LR warm up was important somehow. He had used exponential moving average. Is that the right? Is that the right thing I remember? Hopefully. Now he takes you to Tim's EMA module, which I'm not going to open. So I'd used EMA, gradient check pointing, and mixed precision. Now this is like a cool discussion, right? Like I'd also hosted all the top Kagglers on a panel, but like most of the times I'm also myself like, hey, when like do you really care about cosine learning rate versus linear? Do you really care about like how many warm-up epochs? Clearly here you do, right? Like normally you're like, and like it will converge eventually, like as long as you don't care about the training hours. But if you're using such a modified uh, model or such a modified definition, you care about making sure it converges. So here you have to like really experiment, and it takes like some level of expertise or intuition to know that hey, this module or this model should converge. So might as well experiment with warm up, experiment with batch norm, experiment with layer norm. Like I would just assume, oh, like I'm just like being very crazy with this idea, it will not converge. That's that's the difference between Camaro and me. So for inference, he had loaded with CV2. He says PyTorch data loader doesn't work well, and he had used imutils as well. He had used different image sizes. It's faster to create small images by resizing, and he had done overlapping predictions. His model predicts 64 frames at the same time, but the predictions around the edges are inaccurate. So he had done this overlapping predictions where he would discard these last and first eight frames. For post processing, he had simply applied NMS. And for ensembling, he had prepared various models with different folds, and he had ensembled six such models. For him, cropping around the ball did not work. Crop out no player area did not help him. Feed the heat map of the ball did not help, which is curious to see, right? Like after reading, you're like, oh, maybe this should have worked, but it did not. Pseudo labeling also didn't work for him, and he says many other things which we won't find out. So this was the third place solution. Let's move on to the fourth place now. It says public fifth, but if you look here, it was fourth on the private. I think this was quite a short read, so let's read through this. He had used Tilly's notebook, which I pointed earlier in the live stream for training. He had used grayscale images as well and done center crop. Difference from previous frame and apply absolute. I'm not sure what he means by apply absolute. Has anyone asked in the. This looks like it. I modified the scores and added. I think it's a setting you have to apply in CV2. Please correct me if I'm wrong about this, but I don't know what absolute is. I'm assuming that's what it refers to. It's a setting in CV2. I might be wrong about that. So if anyone knows better, let me know. He says due to small amount of training, it would be useful to extract video features, three class classification by different efficient nets with input of 11 channels in total, and finally a five model ensemble. He shares the augmentation in detail here. Nothing really pans out. I say pans out because, sorry, he's using zooming and panning. He shares it in detail, and what that allows you to do is the following. So you can see that it creates this effect similar to recording the video or like looking at the real live streams. So he had figured out how to reverse engineer those uh, augmentation. You can look through those. They are really simple, but stacked together, they cause that effect. For labels, he had used a Gaussian distribution, and three these soft labels are the same for three events. Binary cross entropy was used as a loss function. Finally, for speeding up inference, he said he spent a lot of time trying to parallelize CV2 functions, but it did not work. Finally, he used CV2 for video encoding, and grayscaling and resizing was applied on CPU. Then difference, absolute, and input batch were done on GPU. This allowed him to run six models within the time limit, and due to margins, he only submitted an ensemble of five models. You can see the scores here, and this was the fourth place solution. On to the fifth place solution now. It says public fourth, but it was fifth on the private. So they do to switched their positions. Although I don't remember how much the difference was. I think it was quite short or quite small in this case. Fourth and fifth. Yeah, really small difference. So their approach is extracting frames, candidate frame selection, event area detection, and event classification. And here they show the different blocks and the models and the backbones they had used. You can read through this if you like. Frame extraction used FFmpeg to extract and save the frames. For frame selection, the purpose is to find candidate frames in which events are likely to occur. They had simply classified each of the extracted frames to four classes: play, challenge, and throw in. And the backbone was efficient at V2 large. This process did not use the time information, so accuracy was not high. But he wanted to find the event with a high recall. So he ignored the absolute values. Event area detection. Through a set of experiments, he found that it's difficult to reach a score if he naively used entire frames. So he manually, I think, labeled all of these frames, which is cool to see. He annotated XY coordinate of an event area, and this took several weeks. The event area detector is a simple unit and it outputs a heat map of the event area. He had used a B5 and an image size of 512 by 512. And he shows the output later on. You can see that it accurately detects what's happening or where the event is happening. He decided against detecting the ball and only stuck with detecting the events. For event classification, he says the frames from candidate frame selection contains a lot of non-event frames and they are not reliable. So he applied a more sophisticated recognition model. He ended up on the 3D channel separated network CSN, which had shown good performance earlier. I think it was in the NFL competition where we saw this. And did I live stream about that 2 weeks ago, 1 week ago? I don't know. You can find that on the channel, but we saw this model about 2 weeks ago as well, I think. He says the training set for this was created based on outputs of candidate frame selection and event area detection. First, he applied the frame selection to all frames and then set labels to background for wrongly selected non-event frames. Then he extracted a ROI for each frame, region of interest. And the center of ROI is the peak of output heat map. He randomly selected about 10% of background frames every 5 epochs. The backbone of CSN is a ResNet 125, and the output and the number of input frames is 16. At training and inference, ROI is extracted from candidate frame, and this is fed to a CSN. So he talks about the computation time later and shows the computation time for each step. To re-summarize, he spent a lot of time manually annotating the event areas. So he extracted the frames and then trained a model to detect the area of interest where something is happening. And after that, finally classified that with the CSN model. So this was the fifth place solution. On to the sixth place one. Says it's a simple approach based on public notebooks. The summary is that used a baseline notebook for processing pipelines. Similar to public first, they had three neighboring frames converted into grayscale. And they say this was like probably the crucial area. Finally, applying high resolution images, modifying loss functions, augmentation, and ensembling was key. So the figure shows the flow of this technique. So they have all of these three frames converted into grayscale, concatenated into a channel, and input into the model. They share the training settings for different folds, the input size, and apparently it's efficient at B0 and B1 model, the Ensemble 2 models. And later they share the scores for all of these different models and what they ended up doing here. So there are some fine nuances here as well, which is like that use color jitter, and they had changed the interpolation method for resizing. So for context, when you resize images, you have to pass in arguments into the CV2 function if you're using CV2, that is. And you can like select different functions. So apparently this was important, maybe. They also created a custom data loader to prefetch images. And they had tuned the parameters for window size and ignored width in make sub function. Do they clarify what is the make sub function? No, they don't. So this is like a mystery. All right. So you can see that they started with Tito's baseline, added TTA, fixed the label error, used three neighboring frames, changed the size for every two frames, added BCE loss, added a custom data loader, added data augmentation, and I think this like got them to gold already. Replaced B5 with B0, changed the size, mix up, replaced three models with full fit models, and finally got to a really good score. So this was the sixth place solution, iteratively improving upon the public baseline and getting to sixth place on the private LB. Let's take a look at the seventh place solution. We might again go 10 minutes over the time limit, which is becoming very regular. I don't think anyone would be surprised. Seventh place solution is quite short. Most top solutions are 2.5 or 3D classification. For some reason, this person assumed that it can't be that simple. So, in short, they detected the ball, tracked it, classified the area around it, and did not ensemble. He used a solo detector and solo classifier, used all the frames in original resolution, which is full HD. To be more specific, he had used images from clips and manually annotated them. Firstly, it was only ball detection, but then he was successful only with classifying play events. Then he added a second class of throw inner to his detector. He also used synthetic augmentation, removed actual throw inner, applied image in painting to create an additional throw inner, used Kalman IOU tracker to keep ball position visible, used 3D classifier with four classes, stacked center frame plus minus 12 frames, and classified overall 25 frames. What was helpful? Changing from 2.5D to 3D, introducing throw inner class, and synthetic data generation. We're seeing more and more GANs being used everywhere, right? Like, I'm sure we'll see stable diffusion soon in a competition. I don't know. But it's cool to see image and painting being used here. Um, it was close to 9 hours for them, and finally they shared other issues, which was using file video stream helped him save the time. So to simplify, it was a four-step process, no ensembles, slightly sophisticated, but it's cool to see that he had used image in painting and also classified all 25 frames together. This was the seventh place solution. I think I can wrap up around here. The 15 place solution is a very short write up, and this might be cool if you're interested in looking at videos. He shared how Kirk shares how he had sped up the speed of feeding the videos, and it basically like tells you he had rewritten a lot of different things and custom data loaders, which got him to like an insanely fast reading or like feeding speed. And there's also the 34th place solution, which is cool to see because they talk about pre-processing and different techniques they had applied. But I just give like a one-liner overview of these two. You can read through them if you want. I think we can wrap up here. Just one thing to remind you all. So next Friday or this coming Friday, we're having the study group around the Hugging Facebook. So you can like remind yourself, just go to this tab and click on remind me so you'll be notified. Just notify yourself if you want. We'll start by reading the Hugging Facebook one chapter every week, and I hope to like cover that in about 6 7 weeks. And in about 40 days, I'm hosting all of the quadruple GMs. So that's a 10K special, 10K subscriber special event that I've managed to pull together. Thanks for joining me again this weekend. Next weekend, we'll read through the auto solution, which is a Rexis competitions top solution. All right, we'll keep meeting every weekend at the same time for at least a few weeks now. Thanks for watching.